Hi everybody, my name is Mackenzie Hall, and today I'm going to be presenting my College of Engineering Senior Design project, as well as my Kilachand Honors College Keystone project, titled the Ciprometer, a device for detecting environmental antibiotic residues in low-resource settings. Antimicrobial resistance, or AMR, is one of the most significant threats to global health in the modern world. As shown in this purple bar on the graphic to the left, it's estimated that if nothing is done to manage it, it will be the direct cause of nearly 10 million deaths every year by the year 2050. For reference, cancer kills about 8.2 million a year now. So in just 30 years, AMR is predicted to cause nearly 20% more deaths than cancer does currently. So this burden is especially acute in low-resource settings, or LRS, as shown in this map showing the predicted distribution of these 10 million deaths. The darker colors indicate regions of greater mortality, which, as you can see, tend to overlap with lower resource areas like Asia and Africa. So these regions don't have the resources to deal with these resistant outbreaks, nor the regulation to prevent the misuse of antibiotics and environmental contamination, which drives the development of AMR. So resistance generally develops when bacteria are exposed to a subtherapeutic dose of an antibiotic. A therapeutic dose of an antibiotic will kill the entire population. A subtherapeutic dose will not kill every bacteria in a population and thus will provide an opportunity for adaptation and apply a selective evolutionary pressure to encourage the development of resistance, such that even if you come back at that with a full dose of antibiotic, you will now be unable to kill those resistant bacteria with that drug. So this has been closely studied in the context of the human body, which is why you're always told to finish your course of antibiotics when you're sick, but less while studying the environment. The general rule is that if there is a subtherapeutic dose of antibiotic interacting with a bacterial population, it will encourage resistance. And this can happen anywhere, including both in the human body and, for example, in a river. So for our project, my team and I have decided to focus on ciprofloxacin, or Cipro, a broad-spectrum antibiotic that is frequently misused in both humans and animals. If you guys are interested in hearing more about why we chose Cipro, please feel free to ask during the Q&A. So Cipro can get in the environment in any number of ways, most of which occur more often in low resource settings than they do around here due to regulatory agencies like the EPA in the United States. So human waste entering soil and water can have Cipro in it. Waste from drug production factories and the dumping of old or defective pills into rivers or soil can introduce Cipro into the environment. Agricultural uses are a particularly acute issue due to prophylactic use of antibiotics to encourage growth. So farmers will fill their entire water or feed trough of their animals with Cipro, meaning that healthy animals are getting high doses of these antibiotics, which they then shed in their waste, and when that feed trough is dumped, all of that leftover Cipro is dumped into the environment along with it. So it's widely understood in the field that environmental contamination of antibiotics will contribute to AMR development, but it's never been definitively proven. It's easy to observe that when you give a patient less antibiotic, they're more likely to develop resistance. It's much harder to see that when a Cipro factory is dumping its byproducts into the river, the communities downstream are more likely to have Cipro-resistant infections. It takes more data and more research to establish that connection, and as of now, there's no device out there designed to facilitate gathering this data. There is a significant need for us to develop a way of measuring environmental antibiotic contamination in order for us to prove beyond a doubt the connection between contamination and AMR. Once we have that data, it'll be able to drive policy and regulation worldwide. So our device, aptly named the Ciprometer, will be designed to provide that data on ciprofloxacin contamination. So as of now, there are really only two existing technologies in this area. High-performance liquid chromatography, or HPLC, is highly accurate and quantitative, but it requires a huge, expensive lab space, trained personnel, and expensive reagents, making it completely infeasible for use in low-resource settings. Minilab, on the other hand, is more portable, it's cheaper per test, but it can't run environmental samples, and it can only determine if Cipro was present or not, and can't provide any quantitative information. So our device will be designed specifically for low-resource settings, where these issues are most acute, in that it will be portable, low-cost, and quantitative. It'll be able to quantify Cipro contamination in these environmental samples and generate much-needed data to contribute to the global dialogue on AMR. So to create this device, we've broken our goals down into two aims. Aim 1 is to create a methodology to quantify Cipro. So my group and I decided to build off of past work done in the Zaman lab, in which a chemical fluorescence assay was developed for Cipro detection. For this assay, when you mix Cipro dissolved in water with a probe solution made of several different chemicals, you get a fluorescence output. So this fluorescence changes as concentration changes, so you can use that measurement to work backwards and determine the concentration of an unknown Cipro sample. Our second aim was to create a field-ready, user-friendly device which can take an environmental sample and run the assay from aim 1, and then output what concentration of Cipro was found in that sample. So we would love for this device to be portable enough that it can perform tests in the field, and we want it to be robustly designed such that it will operate well in low resource settings. So this means that we want to use easy to obtain, less expensive parts and design it in a simple way such that users won't have to perform regular expensive maintenance. Our target users are researchers and regulatory agents, so we've designed the device such that it's user-friendly for these populations. Here you can see a mock-up of how my team and I envision the device. The user interface will be simple. An LCD display will prompt the user through the various steps, and the users can toggle through using the buttons to the left and right. When the user obtains an environmental sample, they can insert the sample into the filtration syringe, pipette the prompted amounts into the sample channel, insert a probe cartridge into the probe channel, and press a button so the camera will read the excited fluorescence from the LED. The device will then output a quantitative result on the amount of Cipro in the sample on the LCD screen. So now I'll go into a little more detail regarding the way that we plan to quantify Cipro in a sample. So when probe and Cipro solutions are mixed, the camera reads a fluorescence output. So this graph shows the ranges of fluorescence outputs from different Cipro concentrations ranging from 10 to the negative 6 milligrams per milliliter to 9 milligrams per milliliter. So the blue bars represent a range. The bottom of the bar is the lowest fluorescence output we read from a particular concentration, and the top is the highest. So we've decided to use these ranges to quantify Cipro concentration instead of an equation of fit, because as you can see, there's not really an easily discernible pattern, and there is a wide variation within just one sample. As you can see, these bars overlap quite a bit in certain areas, so our device would have a hard time discerning between, say, a sample with 7 times 10 to the negative 3 and 9 times 10 to the negative 3 milligrams per milliliter. However, when you group similar concentrations together, a clearer set of ranges emerge. So here you can see the same data from the previous graph, but the ranges now include all concentrations of a particular power. So the bar labeled E-3 shows the range from the lowest to the highest concentration from samples containing 1 to 9 times 10 to the negative 3 milligrams per milliliter. So as you can see, these bars are much more well-defined and separated than the bars on the last graph. So we'd be able to more easily discern what concentration a particular fluorescence value is associated with. So this data is still very preliminary, and before we would move further forward with this project, we would have to perform quite a few more experiments to establish these ranges and prove that this method of quantification is accurate with statistical significance. So the point of having this data is to know when Cipro is present in the environment and how severe the contamination is. So it's not terribly important that we know the exact concentration. Knowing that Cipro is present in a river on the scale of 10 to the negative 3 milligrams per milliliter essentially has the same implications as knowing is 3 times 10 to the negative 3 milligrams per milliliter. So we have determined that our device should output its results as a level of contamination rather than as an exact concentration. So in the very beginning of this presentation, I told you all a simple statistic about AMR. 10 million people are estimated to die every year from causes directly attributed to AMR by the year 2050. That's one person every 3 seconds. Before we can fight the threat of AMR, we need to prove what's causing it. Antibiotic contamination in the environment has not yet been directly linked with AMR, and this means that its catastrophic effects continue to worsen the threat of AMR as we speak. The quantitative data from the Ciprometer can lead to a proven causality between antibiotic environmental contamination and AMR, allowing for a more targeted approach for policy reform and standardization of antibiotic use, particularly in low-resource settings where these issues are more widespread. So this reform would 1. Limit antibiotic prescriptions to humans and use in livestock, 2. Further develop sanitary infrastructure in communities and in farms, and 3. Strengthen the regulatory framework to enforce and oversee these changes. The Ciprometer is a quantitative, portable, and cost-effective device to contribute to the global dialogue on AMR and facilitate these urgently needed solutions. So I'd like to extend a special thank you to Dr. Mohammed Zaman, my mentor, and the entire Zaman Lab, as well as my partners Julia Cirillo and Tiffany Yang Tran for everything they did to help develop this project. Thank you all so much for listening, and let me know if you guys have any questions.